I'm here to present our CVPR paper, which extends the Euclidean multinomial logistic regression, known as MLR, into the SPD manifolds for better classification. So in computer vision, there are many features like in SPD manifolds or symmetric positive definite matrices, such as medical imaging, action recognition, brain computer interfaces, or radar classification. So there are several networks where the hidden and the input features are SPD matrices. The most of the networks relies on the classifier on proximity spaces, such as the tangent space or coordinate system. So their classifiers will distort the inner geometry of the manifolds. So in this paper, we propose the Riemannian classifier directly based on the geometry of SPD manifolds. So we have three contributions. Firstly, we give a general framework or expression for SPD MLR under PMs. PM means the metric pullback from a Euclidean space. So we specifically showcase our framework under the LCM and LEM, two popular Riemannian metric on the SPD. So, and we also give an intrinsic explanation for a very popular tangent classifier, which is the log-E classifier. So here is the Euclidean MLR. Previous work have the Euclidean MLR composed of the FC layer and the softmax. So previous work have reformulated the Euclidean MLR in by the distance to the hyperplane. So the zero SPD MLR has extend the Euclidean MLR into SPD manifolds by geostructures, but the geostructure was induced from the Riemannian geometry, and also not every metric have a geostructures. So in this paper, we found that for the PM, it's not necessary for geostructure. We can directly get the closed form expression. So also for the zero MLR, the solution should be solved case by case, but we directly give the general solutions. So here is how we do it. So here is how we achieve this goal. We first reformulate the hyperplane and the MLR into SPD, shown in definition 3.1 and 3.2. So the hardest point is to solve the distance to the hyperplane, which is an optimization problem in the EQ14. So basically, we are solving the EQ14 under any PEM. So before we show the solution, we also want to point out that our definition 3.1 about the SPD hyperplanes are meaningful because the SPD hyperplanes are submanifolds, and the submanifolds are natural generalizations of Euclidean hyperplanes. So lemma 3.5 showed the solution for the distance to hyperplane, and we also talk about the optimization. Combining all the results, we can get the theorem 3.8, which is the MLR under any PM. So for specific MLR, we just need to put the pullback mapping phi into the EQ19. So this is how we get the MLR under LEM and LCM. And the figure 1 shows the different kinds of hyperplanes under different metrics. So for a very popular classifier, which is composed of the matrix logarithm, FC layer, and the softmax, it implicitly respects a Riemannian classifier, which is described in this proposition. So here is our experiments results. We found that our classifier achieves better performance with minor extra computational cost. So our paper and code is publicly available. Thank you for the listening.